I'm Yuanchao. I'm from North Carolina State University. I will introduce our work called MERR, Improving Security of Persistent Memory Objects via Efficient Memory Exposure Reduction and Randomization. This work is a collaboration with the University of Central Florida. In the traditional memory hierarchy, DRAM provides a good performance, but the data is volatile. The data in the disk is non-volatile, but accessing disk data is slow. Now there's a new technology, persistent memory. It combines the advantages of DRAM and disk. Persistent memory provides DRAM-like performance, non-volatile, and high-density features. Processors can just use regular load and store instructions to access persistent data without the serialization of file system calls. Persistent memory can also keep the fruitful data structures as persistent data to avoid reconstructions. However, when we enjoy the benefits of persistent memory, we also meet a security problem. The security in the persistent memory is more important. Without system calls protection, like open or close files, the attacker is able to use dangling pointers to perform unauthorized read and write to a victim data. And after they corrupted the data in the DRAM won't be propagated to other processes beyond this process lifetime. However, the corrupted data in the persistent memory is able to propagate to other users beyond its lifetime. To improving the security of the persistent memory, we propose an idea called memory exposure reduction and randomization. In the traditional program, the program will malloc the data and then perform several accesses. After the last access, the program will free that data. Between the malloc and free, the data is memory mapped to this process. We regard this memory is exposed during the malloc and free. This period of time is called the memory exposure. And the attacker is able to use the vulnerabilities to launch attacks during the memory exposure. Our idea is to reduce the memory exposure into several small temporary windows. When the data is not mapped outside this temporary window. Every time when we open a temporary window, we also perform a runtime randomization. In this way, when the attacker won't try to launch the software attacks outside the window, they will just receive the segment fault because the data is not mapped. Even though they can obtain some information in the previous window, like memory layout information, those information will become useless in the next window due to the runtime randomization. Our method is not specific to a particular kind of attacks. We generally reduce the vulnerabilities to perform software memory disclosure and corruptions attacks. To efficiently support this idea, we designed the MERR, it including a simple but efficient page table design and a novel architecture support. To combine this two design, it can overall reduce the 70% memory exposure rate with 10% overhead. Meanwhile, it provides a maximal 80 microseconds temporary window. At the same time, it provides 100,000 randomization frequency with similar overhead compared to the state-of-art data randomization work. The following presentation including the attach and detach system calls introduction, page table design, randomization, architecture support, and evaluation. One programming model of persistent memory is to use attach and detach system calls. The persistent data is organized as the persistent memory objects in the physical address space. When an attach system call is invoked with the PMO ID and the permission, the process will just initialize PTEs that points to this PMO, and then the process is able to access this PMO. And we assume the system calls already have the relocatability support. This support can be either hardware or software support. When a detached system call is invoked with PMO ID, this process will clean these bits and then the data is removed from the process address space. However, the overhead of attach and detach system calls is not small, because the current system uses a hierarchical page table. For a 1 GB PMO, when an attach system calls is invoked, it needs to initialize 1 PTE in level 3 directory and 500 in the level 2, and 200,000 PTEs in the level 1 directory. And the memory access to a recently mapped PMO will also incur the page faults. The challenge is how to support the attach and detach system calls efficiently. Our idea is to also keep the page table subtrees as a persistent data in the PMO, and we embedding this page table subtree as a part of metadata of this PMO. Now, when an attach system call is invoked for even 1 GB PMO, the process only needs to initialize 1 PTEs. Then the PMO is mapped to this process. The process can just use regular load and store instructions to access the entire PMO under the permission control. When a detached system call is invoked to this PMO, the process also only needs to clean 1 PTEs to remove this PMO from process address space. Then the process no longer can access any data in this PMO. And whatever how large the PMO is, the attach and detach system call will only need to modify 1 PTEs to perform add or remove the PMO into or out of the process address space. And based on this design, we are able to perform faster address space layout randomization. We call it PMO space layout randomization. For attached system calls, the random selector can select one of many possible PTEs. Then it can just initialize one of them. The randomization is finished. For the relocatability support after the randomization, we assume the persistent program model already have that in the software or hardware. Then seems like they have all memory exposure reduction and randomization support. But however, a new problem is encountered. The problem is the permission control of the PMO. When the process finishes the attached system calls as previous step, actually the request read-write permission is not actually support. In the current system, the permission is per page permission, which is checked in the TLB, but that is stored in the last level page table directory. We can use like a default permission of the PMO, but when the request permission is different from the default permission, all the last level PTE need to be changed. Moreover, when a PMO is shared by two processes with different permissions, one of them needs read-write permission and another needs read-only permission. We only have one embedding the page table subtrees. It cannot support such a scenario. So therefore, we propose an on-chip permission matrix per core to support process-wide PMO permission in different processes. The basic idea is following. The load and store instructions will use the virtual address to check against both TLB and the permission matrix simultaneously. Then the process-wide PMO permission and the page-level permissions are obtained. After that, the access will check against the most strict permission among these two to decide whether this access is legmatic. Entries in the permission matrix are added by attached system calls, and they are removed by detached system calls. The basic design of this idea is following. For an attached PMO, the entries of this PMO in the permission matrix will have for a virtual address start and a virtual address range to represent the virtual address range of this PMO, and also its permission of this PMO. And there are several entries in the permission matrix, and the virtual address need to check against all of them to find a match, so it will incur a high overhead because the permission matrix check is on the critical path. Even several cycles overhead is also critical. Even though we can use the content addressable memory, that the speed is still slow. To solve this problem, we propose a virtual address tags to check against the virtual address. Let's go back to the page table. For a PMO, when the size is larger than 4 kilobyte but is smaller than or equal to 2 megabyte, during the attached system calls, level 2 directory entries will point to embedding the page table subtrees in this PMO. And the directory is also page aligned, so some of the entries above entries in this directory page will point to the actual data, and some bottom entries are actually invalid. The virtual address start that is the virtual address that the first valid PTE points to, and the virtual address end is the last valid PTE that points to. But actually, those invalid PTEs will not used by the process address space because that is an embedding the page table subtree that is not the process address space. Then we can partition the virtual address into two parts. The prefix is used to locate the last level PTE outside the PMO page table subtree, and the suffix is used to locate the PTE inside the PMO subtree. And all the data in this PMO can use the same size of the suffix to locate the data. Then we can design the virtual address tags to represent the virtual address range of a PMO. The virtual address range tags has two parts. First is the prefix as we introduced previously, and the second part will just represent as several X. That X means all match during when it compared against with the virtual address bits. Then depends on the PMO size, the suffix will have different width. For the PMO for a PMO has 4 kilobyte the data, it will only have 0 bits suffix. For the PMO that is larger than 4 kilobyte but smaller than or equal to 2 megabyte, the virtual address tags will have 9 bits X suffix that can represent all the virtual address of such size PMOs. For the PMO is larger than 2 megabyte but smaller or equal to 1 gigabyte, the virtual address tag will have 18 bits suffix, and it can also represent all virtual address with such size PMO. And those virtual address tags are non-overlapped. With this tag design, we can use content addressable memory to locate its permission in one shot. The permission matrix in this way, the permission matrix entries will have the virtual address tags and the permission, and when the regular load and store instruction is invoked, the virtual address is compared against all entries in the content addressable memory. The permission is derived when there is a match in the permission matrix. Then it is time to evaluate the whole design. We use the Whisper benchmarks to evaluate our results. The benchmarks are built from the real-world persistent memory applications. For the operating system overhead, we implement attach and detach library to replace the memory map and memory unmap system calls. and we obtain such operating system overhead in a real machine. And we use trace-driven simulations to obtain the architecture-related overhead. We mainly use three metrics during the evaluation. First is the attached memory exposure rate. This represents the overall reduction after overall exposure time after the reduction. And the second is the memory exposure window. This represents the size of a temporary exposure window. And the third one is the PMO space layout randomization frequency. We will present how much time a PSLR is performed. And in the examples, there are 3 times randomization during the whole execution. Let's take a look of the performance overhead. The value of these 3 metrics are strongly related to the overhead. There are many sensitive studies in the paper of these metrics in the paper. Now we will only introduce that with 10% overhead, our design is able to reduce 70% memory exposure rate and a maximal 80 microseconds memory exposure window. The randomization is performed every 41 microseconds on average. And then how much efficiency we actually obtain from the whole design. To achieve these goals, to achieve above goals, the basic attach and detach method overhead is linearly with the size of the PMO. For a 1 GB PMO, our method is 2000 faster than the default attach and detach system calls. And how is our performance compared with other related work? The enhanced ASLR provides a heap data runtime randomization. And at the 10% overhead, our frequency is actually 100,000 higher than the state-of-art heap data randomization work. And there are more results in the paper. And let's take a look of the security analysis. For a non-protected program, the attacker needs to probe to get some information and weaponize the attack and then launch the attack. The attacks typically need 10 milliseconds at the probe stage. When there's a one-time ASLR support, attackers just need more seconds to probe the information. With our 80 microseconds maximal memory exposure window, when the attacker probe outside the window, they actually perform a false probe since they will just receive the error. And even the meltdown can bypass the kernel space layout kernel space isolation. It can still not read an unmapped data. Combined with the PSLR, the memory layout information is changed every time when the data is exposed. So the memory layout information the attacker obtained is invalid every time when they are able to perform a real probe. So they only have 80 microseconds to attack surface to perform attacks. So there are more examples and analyzed in the paper. In conclusion, we propose a new angle to improving the security through memory exposure reduction and randomization. We improve the efficiency by page table design and architecture support. We are able to achieve 70% memory exposure reduction, 80 microseconds temporary window with 10% overhead, and we provide an order of magnitude speed up compared to the state-of-art runtime randomization work. And thank you for listening our work. We are welcome to ask questions at Slack.